So today we'll be going over the Mark and Recapture Lab. The goals of this lab is to learn common mark recapture methods for estimating population size, to learn the assumptions of mark and recapture techniques, to describe the conditions that provide for the best population estimates using mark recapture, and to learn common techniques used for mark recapture methods. So this is understanding population patterns. So how do we know if a population is heading towards extinction? How do we know if and how competition is impacting population? How do we determine if impact of population density, disease, and independent factors or temperature on a population? To understand how populations change over time, space, and across different abiotic and biotic factors, we must be able to accurately determine the number of individuals in a population. So a definition of a population is a single species that is usually comprised of multiple populations with some amount of gene flow. So the example down here is populations of beetles at various locations at the Finger Lakes regions in New York. So these populations, as shown by the graphs, change over time varying. Some have more, some have less. So what are some methods for measuring population size? We're going to go over 3 today. So we have direct counts, we have plot sampling or area based, and then we have mark recapture. For direct counts, it is the most direct way to determine the number of individuals, and in general it's like the most difficult way to count populations. However, for sessile creatures or species, such as this barnacle-covered rock, they're not moving and it's in a small area, so it's easier to count than, say, this crab-covered road, because there's a lot of individuals over a large area, and they're moving. So if you count one and it moves to the area where you're counting, you could count it twice. It's just a really hard way to determine a population. So let's do some practice. How many rabbits do you see? It's not that hard, right? Now imagine if these are actually moving creatures and they were ducking and weaving between the grass running around. It'd be a lot harder to count. So let's do plot sampling, or area-based counts. This is the most common and effective way to estimate population size is by direct counting the number of individuals in a given area or volume. So the areas are random subsamples of a larger area. The total population size is estimated by using the average number of the smaller areas, then expanding it to cover the total area. So what is a plot? A plot is a focal area or volume of space that is smaller than the entire area. Plots should be randomized and replicated. So here's a practice. We'll go over the answers in a second, but please pause and do this individually. So, how good is it to estimate? Given that we are estimating using a fraction of the total area, the actual population density is not likely to be exactly equal to the estimate. We can use statistics to quantify the accuracy of the estimate and give us some idea of how confident we can be in our estimate. So the 95 confidence interval is where S is the standard deviation of the samples and N is the number of plots total. So the graph right here shows us the 95% confidence interval of a double-sided bell curve. So back to our example earlier. In that example, the average density was 5 per plot, the standard deviation was 1, and the number of samples was 3 plots. So our 95% confidence interval is 1.13, which would mean that our density as 5 plus or minus 1.13. That means that in our 95% confidence intervals, the density lies somewhere between 3.87 and 6.13. So there's some assumptions you make when plot sampling. The first one is that sample plots are selected at random from the entire region for which the density estimate is meant to apply. Number 2 is that all individuals within the sample plot are counted. And number 3 is individuals do not move between plots during the study.